cover is initially a quick introduction to ITM for those of you who don't know us. I'm going to talk about how markets separate by scale, in our view, and then how we've gone about developing a 10 megawatt module, which is replicable up to 100 megawatt scale. I'm also going to say a few things about system efficiency and considerations thereof, and also give you an outlook on our cost expectations. Starting at the top, ITM designs, manufactures, and sells electrolyser systems. They are rapid response and self-pressurizing and available at a megawatt scale today. They interface with the grid and can provide grid balancing services, and also can assimilate intermittent renewable power. On the hydrogen downstream side, we are servicing primarily energy storage applications through power to gas, and also clean fuel for providing to vehicles. As a quick overview of our recent achievements, we have done around £16 million worth of business last year, which is double what we did the year before. Crucial to that is we've hit the EU long-run cost target of €1 million per megawatt, and that enabled us to sell 5.25 megawatts of electrolysis, large-scale electrolysis in that year. And to put that into perspective, in the first 11 weeks of this year, we've contracted another 3.5 megawatts of electrolysis. So our systems are characterized by, firstly, being rapid response, and that means being able to switch on or off or modulate their power consumption in less than 1 second. And they are qualified for both primary and secondary grid balancing services in the UK and Germany. They're self-pressurizing. They're also very efficient. Two of our customers, the Tuga Group and RWE, have released their own efficiency measurements of our systems of 77% and 86%, including heat recovery. We are offering megawatt modules today, and we have gone through all of the compliance work for deployment in the EU and the US. And we now have over 3 years of operational experience. Key to everything is the stack, and this stack module is on our stand, integrated into a product. You're more than welcome to come and have a look after the presentation. It's based on PEM electrolysis, which operates under differential pressure, with the oxygen side being close to ambient. That saves a lot of money and cost within the system. We have a very novel way of assembling the stacks. There's no tie rods, so it's very lightweight, low part count, and rapid assembly. We operate these things at 55 degrees C, and we consider it to be a very mature technology. The cell area is 1,000 square centimeters. We have 100 cells in a stack, and we operate at 3 amps per square centimeter. Existing product mix today tends to be containerized, but we also offer units which are integrated into buildings. So now I want to talk about scale and how we see markets and applications as a function of scale, our methodology for scaling up, and I want to overview our 10 megawatt module and how we parallel those systems together. So traditionally, large electrolysis has been the arena for conventional liquid alkaline technology, and PEM systems have tended to be pretty small. But the advantages that PEM electrolyzers are offering, particularly in rapid response and grid balancing, has led to a very rapid growth in their demand, and a very rapid growth for demand at large scale. And rapid response, again, is the key. And we see the applications breaking down roughly less than 10 megawatts. It's pilot scale studies, small scale refueling and power to gas plants. As you go up towards 60 megawatts, you introduce the chemicals industry, and higher than that, you're also adding refineries to the mix. So our rationale for scaling up has really been to maintain the modular approach that we've always tried to use. We are trying to use known and defined modules. That means we are not introducing lots of technical risk as we scale up, and we can access larger applications much quicker. We've containerized many of the subsystems because that makes a lot of sense for shipping to site and installation and testing. And we've used a low-cost steel frame construction with a mezzanine floor to minimize footprint. So this is a 10 megawatt stack skid. It sits within a 40-foot ISO container, which is quite a compact footprint. We're able to operate each 2 megawatt module independently from each other, so that gives a lot of flexibility in terms of how the plant is operated and provides for rolling maintenance programs without interrupting operation. We've also got options for waste heat recovery, and we've got a ventilation strategy to make sure that the ATEX case is sound. And if you look at that from an energy density point of view, that footprint represents over 8,000 kilowatt hours for every meter squared if you run that system for 24 hours. So if we spin that round and look a little closer, you'll perhaps see some familiar components. You can see the stacks in there, the skids which hold the stacks together using our dynamic pressure system. We've also got the plate heat exchangers on the roof for the heat recovery, and you can see some of the manifolding for the oxygen and water fluids. If we look at another sub-module, this is the purification arrangement. This is in a 30-foot ISO frame, and it includes both the water purification and the hydrogen purification, which will give you fuel cell grade hydrogen on the output. So in the interest of time, if we put all of those things together, to get your bearings, this is the 10 megawatt skid. We have a separate process water skid sat behind. On the top is the water and hydrogen purification arrangement. We have power electronics in the background, which also includes all of the distribution board and electrical connection points. And we have a cooling arrangement on the outside. The frame of the building sits over the top like that and is clad in a very simple but low-cost way. So by putting all of that together, what we have is a fully integrated 10 megawatt module with drop-in balance of plant. We've designed it in a way where we're minimizing cable runs. We're using polymer fusion welded pipes, which reduces cost and weight. And it's a very compact arrangement. That building, to give you some perspective, is 20 by 14 meters. Scaling up from there, you can imagine, is reasonably straightforward. There's a whole host of layout arrangements to match any particular site. In this example, we've simply extended the building, and then you can do that again to get up to 100 megawatts. And again, for scale, that's 40 by 87 meters. So now a few thoughts on efficiency and cost. The efficiency of the system is a proxy for how much your hydrogen will cost. And so it's very important to understand and optimize the efficiency. And what I've tried to do here is show you a graphic which is indicative of how the inefficiencies in a system like this will stack up. So what I'm showing across the bottom is the load applied to the electrolyser. The dark blue colors represent the inefficiencies that result from the stack. So the harder you work it, the more heat you generate. The top light blue bars come from the power electronics and the inefficiencies in the power conversion, again manifested as heat. And the mid-blue color is a bit more interesting. That's from balance of plant. And this chart represents a constant load of balance of plant. And while the power consumed by the balance of plant is higher up here, it's a relatively small portion of the whole plant power consumption, so it manifests itself as a smaller number of kilowatt hours per kilogram produced. So obviously, to improve efficiency, there's always a driver to make the stack as efficient as possible, but you can only do that while maintaining the lifetime and the cost. With the balance of plant, it's about smart operation and tethering back some of the balance of plant as you operate at lower loads. But it's also worth mentioning, again, heat recovery, because all of this dark blue section and all of this light blue section is recoverable if you have a use for the heat. Something on costs. And what I've tried to do here is, again, give an example. I've tried to look back a little bit in time and look forwards. And we see the demand for larger electrolyzers growing. We also see volume growing. And as we move forward in time, this red line is showing the size of the systems we believe that we will be deploying, which is increasing. And what I've got with the blue bars is how much we think the equipment will cost in euros per kilowatt. And today, at megawatt scale, we're less than 1,000 euros per kilowatt. At a 10 megawatt scale, we feel that we are below 800 euros per kilowatt, and we can see a pathway to less than 500 euros per kilowatt. And that is a combination of physically larger plant, but also more volume and technology improvements as we progress forwards. So to summarize, we have been surprised by the rate of growth of inquiries for large-scale equipment. We see a number of new business models emerging around large-scale PEM electrolysis focused on the rapid response capability. And it really is important to emphasize the value of electrolyzers as a flexible load as part of the value in the overall application. We have developed a 10 megawatt module. We are using a well-known, proven PEM platform that's got many years in the field already. And that gives us a route to access larger scale more quickly and without technical risk. And finally, we see cost reduction through size, volume and technology, and our view is less than 500 euros per kilowatt by the mid-2020s.